in this part, let's talk about the acidity of alkynes, see how they easy they lose their hydrogen. If this is the general formula for a typical alkyne with a triple bond, a hydrogen on the carbon of triple bond, then this is the acidic hydrogen. And with a base like NH2Na, you already know about it. The hydrogen will be picked by the base and the electrons will remain, the electrons will remain on carbon. So such an anion is going to be formed. It obviously forms the ionic compound with the sodium in the presence of this base, and you will have NH3 because NH2 had just grabbed one hydrogen. Okay, so let's see which one of these compounds will have the most, which hydrogen is the most acidic hydrogen, which one will be removed the fastest by a base. This is a carbon here, this is a carbon here, this carbon is connected to a hydrogen. So when we want to compare the hydrogens connected to a triple bond, carbon of triple bond, or carbons of double bond, we know that these are sp carbons, right? Hydrogens connected to sp carbons are the most acidic. So this is a hydrogen which will be removed first with a base. Or the other compound, like if you have something like this, so you see again, you have a proton, a hydrogen from the sp carbon. Of course, these are also good hydrogen to be picked, but first these are the carbons, the hydrogens that are removed by the base. So why is that the reason? If you compare the acidic properties of an alkyne, this is the hydrogen, pK is 25 for an alkyne with the size. pKa for the other compound is, for an alkene, is 44. So this would be the anion, and pKa for an alkane is going to be 60. Talking about this hydrogen connected to this carbon. So okay, so we are here, we are talking about an sp carbon, right, the hybrid, because we're just counting the sigma bonds. Here we're counting the sigma bond, there's 3 sigma bonds, so the hybrid is sp2, and we're talking about 4 sigma bonds here, so the hybrid on each carbon is going to be sp3. So you remember the relation between pKa and acidic strength. The lower the pKa, the higher the acidic strength. So this is the strongest. And this is the weakest. Okay? So why? Because this is the most stable anion, and the last one is the least stable anion. The reason is that for an sp hybrid we have 50% S characteristic, S character, right? 1 to 1 means 50-50, and 50% P. Or let's just put the 50% S. We're just talking about S here. Here in sp2, the percentage of S is 33%, 1 to 2 is 33% S, and in sp3 it's only 25% S. We know that S orbitals are smaller, so electrons are closer to the nucleus in S orbitals. So it makes, the sp hybrid makes this anion and the negative charge more stable on it. So since the S orbital are the closer to the nucleus, they're lower energy than a p orbitals, then this negative charge is more stabilized for alkynes. So we need but still the alkynes, comparing to acids or alcohols, they are weaker acids, but comparing to alkenes and alkanes, they are stronger acids. And we know that we need a strong base to pick this hydrogen, something like NaNH2 or also NaH. These two are good bases to grab this hydrogen. So basically what we need is that a base with the pKa of 25, greater than 25. Like here, NaNH2 is 35 pKa. So we just pay attention to the pKa for base. pKa of base must be greater than 25. So for NaNH2, pKa was, for let's say NH3, because it has to be conjugate acid of base, because pKa and Ka are for acids. Conjugate acid of base. For NaNH2, conjugate acid is NH3, so its pKa is 35. Or for NH, its pKa is it given? 35. I'm sorry, yeah. Yeah, 35, 38, as I see here, is 35 for NH3. So for example, OH or OR are not good because pKa of their conjugate acid is less than 25. Now, we are going to use this property, this acidic property of an alkyne that can lose a proton from the carbon of triple bond in the presence of a base to synthesize more compounds in synthesis reactions. So look what happens. After this is the first step. We have an alkyne, we have to add a base, a strong base to it like NaNH2, and as soon as we get this, I'm trying to synthesize or alkylate a new compound. You react it to a primary alkyl halide. This alkyl halide must be primary alkyl halide. So look what happens. This is your nucleophile. This is your electrophile, right? So the attack is from this nucleophilic carbon to this electrophilic carbon. Bromine acts as the leaving group, and also this is going to react with Br. So we will have RC triple bond, this side from alkyne. this carbon is going to connect to this carbon. So what do you have on this side? CH3 plus NaBr. We don't care about these products, but what is important for us is this major product. So this way we are going to make a larger alkyne from a shorter alkyne, or a longer alkyne from a shorter alkyne. And then you can do the other reactions to make other products. You can add halogen, you can add hydrogen halide, and whatever reaction that you learned before. So this is what we use. We must use a strong base with an alkyne. Then when we have our nucleophile, our good nucleophile, we have to react it with definitely a primary alkyl halide to form a larger alkyne. And don't forget, this is an SN2 reaction, so we need a primary alkyl halide for sure. So these are the facts that you need to know. But what if we do not use a primary alkyl halide? What's going to happen? Look what happens. Let's say you created let's go with the same example as your book. This is your alkyl halide. What type of alkyl halide is it? This carbon carrying bromine is connected to 1, 2, 3. These two are both carbons, right? And this is a carbon. So this is a tertiary alkyl halide. So tertiary alkyl halide is not good for an SN2 reaction, right? So, and suppose that we have added the alkene to a base. Now, this is going to be our nucleophile. So what happens? Then this is going to act as a base. You remember, if we don't have a primary alkyl halide, then instead of SN2 we have E2. So be careful. That's why we emphasize on having a primary alkyl halide. So what happens is that we will end up having, it grabs one of these hydrogens, the electrons remain, and bromine leaves. So we end up having CH2 here and the rest of the products. This is going to grab the hydrogen to form this, and the bromide is going to leave. So as if like you're in the kitchen, you want to make chicken soup but end up having cake, right? Totally different. They're both yummy, but this is not what you were expecting to get. All right. So a little bit more on practice on this. I will go with B on page 9 of this study guide. This compound. First we have NaH, and then we have this alkyl halide. I told you, whenever you have different numbers and reagents on the arrow, means that we need the final product. So NaH is going to separate this hydrogen. The hydrogen is going to attack this carbon. So your final product, if I want to show step by step, let me show it. We will have this, right? This is a negative charge because this is a lone pair of electrons. Then it's going to attack this carbon, and this is going to separate. So we end up having how how many carbons do we have here? 1, 2. So 1, 2. And plus bromide. So what type of reaction is it? Since alkyl halide is primary alkyl halide, so this is an SN2 reaction. Normal conditions. But if you have NaNH2 and then you have this, then this is a tertiary alkyl halide, right? You will end up having an E2 reaction. So the first step is the same, formation of this anion, which is your nucleophile. But here now, instead of, let's say you have CH3, instead of having SN2, then you have an E2. Hydrogen is grabbed, the electrons between carbons, and chlorine leaves. So you will have plus plus okay. Now you have a different product, which is an E2 product. Okay, they're the same. The rest of the practices on this page. And finally, we have the reaction of acetylide ion with epoxides. Reaction of acetylide ions with epoxides. You will learn more about epoxides in organic too, but epoxides are 3-membered rings with 2 carbons and 1 oxygen. This is called an epoxide. So if we want to work on the reactions of epoxides, we have the same. Alkynes that have left 1 hydrogen act as a nucleophile. This time you have an epoxide instead of an alkyl halide. The carbon must attack, and these epoxides are extremely unstable because of the size of the ring, so they are ready to react and pop. So carbon will attack to the less crowded carbon, less hindered carbon. Tell me, between these 2 carbons, which one is more crowded? This one, right? Do you see 2 methyl groups on it? So carbon is better for this carbon to attack this carbon. The bond opens. So you will end up having a triple bond here, these, and then you have this carbon. Show it with the wedge. And here you had 2 methyl groups, and this oxygen was open, right? This bond open on this carbon. Now, in the presence of water, or always when you add water, then you will have OH. Okay? So that's the difference. You will end up having an alcohol with an epoxide and finishing the reaction with water. Another example here could be this one. Adding it to this anion. So in this case, these 2 carbons are exactly same occupied with just 1 hydrogen on each, so it doesn't matter. Carbon here can attack to any of these. So it will attack and or it can attack from here. The attack is from the back of the molecule, less hindered. So you will end up having, with the water also, we finish it when you have it like this, or 1 and 2 on the arrow means we need the product at the end. So we can have OH on this side, and since this is an anti-addition, so you will have the side with, alkene on this side, because this attack to this carbon is going to attach. Or you can have OH on the other side. Doesn't matter which one is in the front, which one is in the back, but normally this anion attacks from the back, but make sure you show them on 2 different directions. So we will have this also. Okay? So whenever there is no difference between the carbons, you have enantiomers, the mixture of enantiomers, both. OH in the front on top, OH in the back. So now we can work on some examples on this page. For example, I'll work on C8, CH3, CH2, CH2Br. This is an alkyl halide. We're supposed to add it to CH3, CH2, C. Okay, so this is going to attack and bromine is going to leave. So this is a primary alkyl halide. So we have an SN2 reaction, CH3, CH2, CH2 from alkyl halide, and on the other side we have C, C, CH2, CH3. Be careful about the octet of the carbons. Don't put CH3 here in the middle. For C, CH3, CH2. If you draw its a structure, it's a tertiary alkyl halide. So with this compound, you will end up having an E2 reaction. An E2 reaction is going to give you CH3, CH2, CH2, CH3, and here you have CH and CH3. Try it, you will see this, because here you will have this carbon has to lose 1 hydrogen, and plus CH3, CH2, C, CH, and you have Na also in the solution, NaCl. If you work on any of these epoxides, let me work on the ethylene oxide. You can work on, or let's work on propene oxide. Propene oxide is different. So propene oxide is this. And it has a methyl group here. So if we work on, what we have is CH3, CH2, C, Na. And then we finish it with water. So we will end up having, this carbon is going to attack this carbon, which is less crowded. Oxygen will be on the same side of methyl. So we will have draw it. 1, 2, 3, 4. 1, 2, 3, 4. And then this compound has 1. Then it has another 1, which is connected to OH and methyl group at the same time, and the rest of the product, CH3, CH2, CH plus Na, and the rest of the products, whatever you have. Okay, the next practice exactly is the same. That's all. Make sure you have enough practice on these concepts.